So, well, I think my estimates of these lecture times are really bad. Like, my actual plan was to finish whatever we have seen before the first break, but it's okay. Well, the advantage of graduate courses is like we don't have the rush to finish any specific syllabus. So sometimes we go fast, sometimes we go slow. But let me know if I'm too fast. So, okay, so we can start. Before that, there are a couple of questions in the chat. First of all, you guys can hear me, right? Okay, so I think there's a question about yesterday's tutorial. I explained that in the beginning, so it did not happen. We are going to fix it and have a tutorial next Tuesday. And there is another question about e power ht going to infinity. So how do we resolve this problem? Okay. I'm thinking. Okay, so I'll think about it and get back to you. Okay, so let's get started. So far, we discussed about simple bandit setting, right? Now, we're going to move towards reinforcement learning, like the full reinforcement learning problem. But there is something in between bandits and reinforcement learning, like which has slightly, yeah?
Do you have any comparison between UCB and this algorithm?
You are going to do that in your assignment. Okay, so the comparison between UCB and gradient bandit, like you will find it yourself in your assignment. Okay, so yeah, so there is something in between bandits and reinforcement learning, the full reinforcement learning setting, which has slightly more complications than just exploration exploitation. So if you remember from the previous lecture, like I told you that there are a bunch of issues that we need to solve in reinforcement learning. Like you have to learn to act in many situations, and there is this delayed reward or dependency of reward issue, and exploration exploitation, right? So we kind of abstracted out the first two issues and just focused on exploration exploitation so far, right? Now we are going to add one more issue, okay? So which is learning to act in many situations, okay? However, we are still in the immediate reinforcement learning setting. So like actions have immediate rewards. They don't affect the next state, okay? But there are many situations to act on, okay? So such problems have a name. So they are called contextual bandits. Okay, so in one extreme we have bandits, okay, which can also be considered as non-associative tasks. Okay, so when I say non-associative task, it means that you don't need to associate different actions to different situations, because there is actually only one situation for bandit. You always have this k-arms, you pull them, right? There is no change in the situation. However, when you have full reinforcement learning, so then you have many situations, okay? Then the goal is actually to learn to map situations to actions, right? So it becomes even more complex problem, okay? Now, what we are going to see very briefly is contextual bandits, okay? So we are not going to discuss about contextual bandits in detail, like I'll just introduce the problem and then we'll jump to full reinforcement learning. So it is worth knowing because there are a lot of good applications for contextual bandits, okay? So now the idea of contextual bandits is like you're going to have associative task, but not all the complications of reinforcement learning, okay? I'll give you an example. Let's say instead of having one 10-armed bandit, I have 10 different 10-armed bandits, okay? At every point in time, I randomly pick one of these bandits and give it to you, okay? Now, if I don't tell you that there are actually 10 bandits in the back, for you, it is going to look like a non-stationary bandit, right? I might have 10 stationary bandits, but in every time step, I randomly pick one of them and show it to you. If I don't tell you that they are different bandits, then for you, it is a non-stationary bandit. So you will go for a non-stationary solution, right? A solution which focuses on non-stationarity, right? However, if I tell you in every time step, okay, now I'm going to show you the first bandit. Now I'm going to show you the 7th bandit. Now I'm going to show you the 6th bandit. So how would you approach? So how would you approach this issue? Yeah.
Work them separately and you apply the
Yeah. So if you know the IDs, then you can separately. The naive solution is to separately do epsilon greedy for all the 10 different bandits and find the optimal action, right? So in some sense, like what I'm giving you is like a context or ID, right? So I tell you with this is this bandit. Imagine bandits come with colors. I show you a red color bandit, then I show you a green color bandit. So then you will start associating colors with actions. Like you will say, okay, whenever there is red color, I should take action 2. Whenever there is green color, I should take action 5. Okay. Now you can see we are slowly getting into the full RL problem, right? Like because now we are talking about situations here. Like so, what should I do when it is red color? Like what should I do when it is blue color, and so on. Okay. Now I can give you an example application. Okay. So in fact, this used to be the only money-making application of reinforcement learning for a couple of decades. Okay. So the application is ad placement. Okay. So given a set of ads, like the goal is to place the most relevant ad for a user such that the probability that he or she is going to click it is high. Okay. Now, as you can see, this is like a revenue generating problem. It is very important that you pick the most relevant ad. Okay. Now, is this a bandit problem? You have.
it depends on the person.
Yes, it depends on the person, right? Like you have 10, let's say there are 10 ads to place. If there's only one person, then this is a 10-armed bandit problem, right? Like, so you want to find which ad they're going to like, right? However, you have millions of users coming to the system, right? So now you have a context here. So the context in ad placement is basically user history. So where is this user connecting from? What are the things that he has purchased in the past? So what is his Twitter account saying? Like, so what is his Facebook account saying, right? You might have a lot of these information about the user. Now, this is a context for picking the right action, okay? So now here you can see that the naive solution of running 10 different or million different epsilon greedy is not actually the best thing that you can do here because users share some context, right? Like, so maybe there's a group of people who like sports. Then you put a sports ad for them, with very high probability they're going to click it, right? So users share context, which means you want to learn these associations, but somehow share information across the users, okay? So how to do that? We're not going to talk about it right now, but we will anyway address it in the full reinforcement learning problem. Okay, so I think this will conclude our discussion on bandits. Okay, so now we are going to jump to the full reinforcement learning problem. Okay, so hopefully when we cut, we are going to cut there and start the next video here. Okay, so for the rest of the time today, like I'm going to formally introduce the full reinforcement learning problem, but through the lens of a mathematical formalism called Markov decision process. Okay, so now this is going to be the fundamentals for all the algorithms that we are going to see in this course. Okay, so observe carefully. So specifically, it's just a little bit of technicality. We're going to talk about finite Markov decision processes or MDPs. Okay. Now, MDP is just a mathematical formalization for any sequential decision-making problem or a reinforcement learning problem, okay? So let's go back to the agent environment loop that we discussed in the beginning of the course, right? Like, so you have an agent, right? And you have some environment. This agent is acting, right? At every time step, the agent takes some action. Let's just call it AT. Now the environment is giving you the reward RT plus 1 and the state ST plus 1. Okay. Now these actions and rewards go to the agent, okay, in the next time step. So in every time step, the agent is going to get reward RT and state ST. Okay. Now the goal of this agent is to interact with this environment like in discrete time steps, like time step 1, 2, 3, 4, and so on. And at every time step, it receives some state. Looking at the state, it takes some action, and it receives some reward on the next state, right? So in some sense, we have this sequence of the events happening, or a trajectory, right? Like so we're going to call this sequence of events as trajectory. Now my trajectory will look something like this. I'll start with the initial state S0. I do some action, and then I get the reward. The next state, next action, next reward, next state, next action, next reward, and so on. Right? Now, as you can see, there are 3 elements in this picture. Okay? States, actions, and reward. Right? Now, a finite MDP is defined by these 3 entities, like states, finite set of states, not infinite, okay? Actions, finite set of possible actions, and rewards, finite set of possible rewards, okay? So they all have finite number of elements, okay? Now, when I say I have a finite set of actions and rewards, right? Then I can actually model them as discrete probability distributions, right? So basically, RT and ST are well-defined discrete probability distributions. Okay, so that depend only on the previous state and action. Okay, so I'm going to define this probability distribution, the probability of the next state and reward given my current state and action. Okay, now this is basically the probability that ST is equal to S dash, RT is equal to R, given ST minus 1 is equal to S, and AT minus 1 is equal to A. For all S dash and S belonging to the set of states, and R belonging to my reward distribution, and A belonging to the action space of S. Okay, now this P, we are going to call this as the transition probability . Okay, but probably I will not call this as transition probability because just S dash given S is the transition probability. Okay, so we're just going to call this as the dynamics function of the MDP. Okay, so in some sense, this P of S dash R given S comma A, right? Like so, this tells you how the world works. So it tells you that given I'm in this current state and I take this action, this is the probability distribution for the next state, and this is the probability distribution for the reward that I would receive from the next state, from this action, right? Now, if you have access to this probability distribution, okay, you can do a lot of things. We'll like, for example, you could ask questions like, if I take this action, so what is the probability that I would get high reward or like this much reward, right? So, and you can ask questions like, if I take this action, what is the probability that I will reach this specific state like which probably has high value, right? So we're going to formalize all these questions. But before that, I just want to make a note that this P function or the dynamics function is a valid probability distribution, okay? So in other words, summation over S dash, summation over R, probability of S dash R given S comma A is equal to 1 for all S belonging to S and A belonging to A of S, okay? This is a valid probability distribution, okay? So in other words, this P function has 4 components. The current state, so the next state, the reward, okay, maybe I'll write it this way. So it's a S cross R cross S cross A. So there are 4 entities, current state, current action, next state, reward. Then it gives you a probability value. Okay, so this is basically a deterministic function of 4 arguments. Okay, now if you have access to this dynamics function, you can do a lot of things, as I said. Like, so for example, like you could compute state transition probability. Okay, which is questions like, for example, what is the probability that I would go to S dash given my current state and action are this? Okay, so how would you compute this? So all you have to do is take probability of S dash R given SA and integrate, like out the R. Okay, so for all possible rewards, you compute this and then like you get P of S dash given S comma A. Now similarly, you can ask questions like, what is the expected reward for a given SA pair, right? So R of S comma A is given by, again, you take the P of S dash R given S comma A. Now you're going to consider all possible next states. This is an expectation, so summation over R. Okay, so now you can easily do this. Now you can also compute expected reward for state, action, and the next state. So I'm not going to do that in the class. You can see that in the notes. Okay. So what I'm trying to say here is like once you have this dynamics function, you can compute a lot of entities with that. Okay. Now, one interesting aspect of this dynamics function, okay, and the MDP in general is the notion of Markov property. Okay. So the Markov property says that the probability of STRT, okay, given ST minus 1, AT minus 1, okay, is equal to probability of STRT given ST minus 1, AT minus 1, RT minus 1, ST minus 2, AT minus 2, and so on. So basically, you can compute this transition probability and the reward function by just using the previous state and action, okay? You don't need to know the history. Or in other words, my current state captures everything from the past so that when I want to take action, I can take actions just based on the current state, okay? So I think I forgot to charge my pencil. So when I'm talking, I'm going to charge it. Sorry. Okay. So now, it might look like a restriction that the current state should hold all possible information, right? Like it looks like MDP is like a very restricted framework because it expects the states to have all the information from the past, right? So however, we should remember that this restriction is not on the process itself. It's more of a restriction on the state, okay? Now, there are many things in play here. Like this is a very flexible framework. Like first of all, the notion of time steps, okay? So we have discrete time steps, right? Like time step 1, 2, 3, and so on. Now this discrete time step need not be the actual time steps, like 1 second, 2 seconds. It could be like varying time steps. Like for example, the first time step could be now, and the second time step could be after 5 minutes, third time step could be after 10 minutes and so, like, or after 1 hour and so on, okay? So, or in other words, these steps are more like steps in the decision-making process, not the physical time, first of all, okay? There is that flexibility. And in terms of actions and states, right? So actions could be low level, like for example, if you have a robot, the action could be controlling the velocity or like torque or like whatever things that you have in a very low level. Like, or it could be very high level. Like, so I can say, talking 3 hours is really difficult. Okay. Or it could be like high level. Like for example, I could just say, open the door or go to the door. This could be the action for the robot, okay? When I say go to the door, then it has to figure out how to walk and go reach the door, right? Now let's talk about states. Now states could be really low level sensations, like what is the current electricity or like what is the voltage, like, and these kind of things for a robot. Or it could be very high level, like for example, like it could be the perception of the robot, like the robot might have a camera and it's the image that is seen in the camera, right? It could be the state. It's a very high level state, right? Like so in some sense, like you have this flexibility of like choosing, you have the flexibility of choosing the state, action, and the time steps. So once you make a decision for that, so then you have this formalism of Markov decision processes, which comes with a lot of nice characteristics, which is what we are going to see in today's lecture and probably in the next few lectures. Okay, so any questions about the setup? Yeah? Oh. Any questions in the chat? Okay, yeah.
Are the states always the same? When we go to the next time steps, are the states are from the same state all the time?
Sorry, can you repeat?
When we go to the next time step, are the states from the same space? Like, they are always the same thing?
Oh, your state changes, right? So every time step you receive a new state. So is that the question?
So, I mean, like, for example, if there are 100 states, if you go to the next time step, do we have again that 100 states and 100?
Okay, I don't understand the question very well, but maybe I'll try to answer it. Tell me if that answers your question. So, okay, so when I talked about time steps, like I was telling you how flexible it is, okay? But in reality, like time steps are decided by the environment. Like, so the environment tells you when to act. Like, for example, let's say we are learning to play the game of chess, okay? Time steps are well defined there. Like, so time step is your next action. Like, you could take 2 minutes or you could take 4 minutes, but the next time step is when you move the next piece, right? So does that answer your question?
The question was more, does the state space change?
No, well, we assume that we have a finite set of states, like so, like it is just that you're seeing the world in different snapshots. That's it. Okay, so now maybe we can continue. Okay, so the other important thing that I want to talk about is the boundary between agent and the environment. Okay, now what is agent and what is environment? Okay, maybe the boundary is not as similar to what you are currently having in your mind. Okay, so for example, like if you're again, let's go to the game of go to the idea of playing chess, right? So in the game of playing chess, like you are the agent, you're taking actions in the environment which has the other player, chessboard, and everything. Okay, now in the case of let's consider humans to be reinforcement learning systems for a second, right? Like so now where does the environment begin? So one obvious answer is like it's anything outside my body, right? But we don't need to restrict ourselves right like that. Okay, so the general principle for something to be an environment is it is anything that cannot be changed arbitrarily by the agent. Okay, and it is considered to be outside of the environment, outside of it and part of the environment. Like so, for example, there may be parts of the robot's body, okay, which has a definite function on how to work, and the robot cannot change it. That should be treated as environment, not as the agent. Okay, so in some sense, the boundary is defined based on the control. So boundary is the limit where the agent doesn't have absolute control. Okay, it is not about the knowledge. Okay, so anything that I don't know, that is not environment. Like sometimes I would know everything in the environment. Like for example, sometimes I would actually know how my reward function is calculated. Sometimes I could see the reward function being calculated, but I cannot change it. Okay, so one important distinction here is that the boundary represents the limit of the agent's absolute control. Okay, not its knowledge. Okay, so sometimes I can face a reinforcement learning problem where I know everything about the environment. Okay, to give you an example, I think the example that we are using, which is borrowed from the textbook, is playing the game of Rubik's Cube. So now you know how Rubik's Cube works, right? So you have all the knowledge, but often we struggle to solve it, right? So why is that the case? Like so it is not about the knowledge. Like so you might have all the knowledge, but still face a very difficult reinforcement learning problem. Okay, but majority of the applications you will not even have that knowledge, which means you have to gain that knowledge about the environment and then act based on that. Okay, now to summarize what we have discussed so far, like about this MDP setting. So MDP is a kind of elegant formalism which formalizes this entire reinforcement learning problem with 3 different signals. Okay, just 3 signals. So you have one signal. Okay, so the first signal, which is to represent the choices made by the agent, the actions. Okay, then you have another signal to represent the basis on which these actions are made, which is the state. Okay, then you have another signal to define the agent's goal, which is basically the rewards. So if you define actions, states, and rewards properly, then you have this nice framework, and we can develop efficient algorithms, as we are going to. Probably we cannot develop any algorithms today, but from next week, we will develop efficient, like scalable algorithms to solve this MDP problem. Okay, there is a question in the chat. So what if absolute control is greater than its knowledge? What do you mean? I'm not, Adam, I'm not sure about, I don't understand the question properly. So what do you mean absolute control is more than the knowledge? Okay, maybe we'll take it offline. There is also a little bit of lag, so maybe my question will reach them only after 30 seconds. Anyways, okay, so now, one thing that I want to highlight right now is, I told you that how important it is to choose the right state, like how to, like right set of representations for state, action, and like how to choose a proper reward function and so on, right? Like so these are important problems. Okay, so designing good reward, designing good state representation so that it captures everything from the past, so I can take action just based on the current state. Okay, designing or parameterizing my action space in a nice way, right? Like, so these are very important problems, but we are not going to talk about these problems for the next few weeks, okay? For the next few weeks, probably 3 to 4 weeks, 3 weeks, let's say, we are going to assume that someone has given us these states, actions, and reward functions, okay? And we will just talk about the problem of how to act optimally given a specific action, state, and reward function. Okay, so this is just to focus on the fundamental problem of the course, which is like how to act, and then we will slowly talk about representation learning for states, like so how to learn these representations, which are good enough, like which are really helping me to take a better action, and how to design reward functions. Probably we will not spend too much time on reward design. Like towards the end, we will talk about reward design and how to parameterize actions. Like so, we are going to talk about all these issues in detail, maybe in the second half of the course. Okay. Now, there's only one thing that I want to talk about: the rewards, though. Okay. So, I think we already discussed this in the first lecture, but I would again highlight the relationship between goals and rewards. Okay. Now, reward is a way of communicating what you want the agent to achieve, okay? Not how you want it to achieve. So you should not inject your prior knowledge about how to solve the task in the reward function, okay? Because that could lead to like unintended consequences. Like if you remember the trash picking robot, like my reward design was a little bit faulty in the sense I was giving it reward every time it picks things, okay? Now I did the mistake of telling the robot what to, like how to achieve my goal. My goal was not picking things. My goal was to keep the room clean, right? But I went a little bit further and I said, okay, every time you pick things, you get reward. So now the agent can actually exploit this faulty reward design, and it could put trash and pick it, right? So that there, this is the classical problem, right? So basically, the rewards are telling agents what to achieve, okay, not how to achieve it. Okay, is it clear? Okay, so now let's talk about returns. Okay. So far, I was always using this term cumulative reward, right? Like so, because I wanted to differentiate the fact that it is not important to just get the next, get immediate but best reward, like best immediate reward, but it is very important that you get good reward throughout your life, right? So we called it as cumulative reward. Okay. A very concise way of saying that is return. Okay, so what is return? So return is basically the cumulative reward. Okay, now, for example, let's say I'm in time step t in a specific state. My return gt is defined as all the rewards I will get starting from this time step. Okay, so which is basically rt plus 1 plus rt plus 2 plus rt, where capital T is basically the final time step. Okay, now here I want to discuss the different types of tasks that we could see. Okay, so in this particular definition of return, I assume that my interaction is going to end at some point, right? For example, if I'm playing the game of chess, then the interactions end when the game ends, right? So it could be after 10 moves, or it could be after 20 moves, or it could be after 50 moves, but the game ends, right? Now we are going to call these ending interactions, right, like as episodes. Okay. Now you can have many episodes of playing the game of chess. First episode, you play the game, you win or lose. Then you go back to the beginning of the game board configuration and you start the process, right? Like basically episodes are repeating similar interactions. Let's put it that way, okay? Now, But this is not the only class of problems we care about. Maybe there are other problems where there is no definite end time. So can you give me some examples of problems where there is no end time? Okay, you can be creative. Yeah?
Investing in stocks.
Sorry?
Investing in stocks, right?
Okay, so investing in stocks, it's a kind of a continuing problem, right? Like, so there is no, well, you hope there is no end time, right? Like, so like you keep on, you want to keep on continuing. That's a very good example. Any other examples? Yeah?
Controlling the position of air balloon for providing internet.
That's another good practical application. So like controlling the position of air balloons that provide internet to remote locations. Now it's a continuous process, right? Like, so you want to keep on controlling, like you don't want that episode to end either. Yeah?
The robot that cleans the room.
Robot that is cleaning the room, like you don't want it to stop working. So there are many situations where you don't have a finite ending episode, okay? Now, in those cases, okay, so this definition of return is problematic. Why? First of all, you can never compute those returns because these episodes are not going to end. So if you want to know their return from this current state, then it's like it's going to be an infinite term at least, right? Like so for most of these continuing tasks, this version of return is infinite. So you are trying to maximize a term which is infinite, right? So which is not a very well-defined problem, okay? So I want to differentiate tasks into two types. So you have episodic tasks and you have continuing tasks. Okay. Now, when I have episodic task, this GT definition is fine. But when I have continuing tasks, okay, I'm going to come up with a new definition for GT. Okay, my definition for GT is going to look something like this. GT is equal to RT plus 1 plus gamma times RT plus 2 plus gamma square times RT plus 3 and so on. Okay, or in other words, summation over k is equal to 0 to infinity r power k, sorry, gamma power k. Okay, I had this problem even when I was writing my notes. My gammas and r's look very similar. So I'm just going to call these as gammas, okay? So gamma power k RT plus k plus 1. Okay, where this gamma, right, which is between 0 to 1, okay, we are going to call this gamma as discount rate. Okay, so this gamma determines the present value of future rewards. Okay, so basically when you are in a continuing task which goes on forever, it is not very important. Let's take the robot, the cleaning robot, for example, right? It is not very important. It is actually not more important to worry about what happens after 1 month, about the lifespan of this robot, than what happens next week, or what happens tomorrow, or what happens right now, right? So in other words, future things, you can worry about them, but at a discounted rate. Now, if I have to give you like an analogy with money, right? So it is actually more valuable to get $1 million today, and it's probably more worth than the $1 million that you're going to get after 10 years, right? So the money that you're going to receive right now has more value than currently than the money that you're going to receive in the future. Okay, so that is the discounting that is happening here. Okay, now how are we discounting? We are exactly discounting with gamma. So for example, if something happens after k time steps, it is discounted by gamma power k minus 1. Okay, now if gamma is less than 1, then this infinite sum has a finite value. Okay, as long as some conditions are satisfied with RK, like RK, like we are going to have some finite value for this return. Okay, now there are two extreme cases here. So we will stop with that. So the first extreme case is gamma is equal to 0. So can someone tell me what happens if gamma is equal to 0? Sorry? So when I say gamma is equal to 0, then we get a myopic agent, okay, which means it is very short-sighted. It is only satisfy, like trying to maximize the next reward, okay. Now the other extreme is gamma is equal to 1. So what happens in gamma is equal to 1?
Future is as important as now.
Every time step in the future is as important as the current time step, okay. So this is a very far-sighted agent, and as you can see, both these agents are not good, right? Like you don't want to be in 0 range, and also you don't want to be in gamma is equal to 1 range. Normally, we will set gamma close to 0.9 or 0.99, okay? Because this is an exponential decay, right? So you want very high value for gamma, but not 1, so that you give some importance to the past, but it decays exponentially, okay? So well, I think we are running out of time, so probably we will stop here. And just to give you some teaser, like so for the next week, like now that we have introduced the MDP problem, like so we will talk about value functions for MDP, and then we will talk about how to estimate value functions and how to come up with a policy to act in a full reinforcement learning problem. But that is probably the point of discussion for the entire course. So we are going to see several ways to solve this problem in the future. So I will stop here, and a couple of general reminders. So it is my office hour up to 1:30. So, well, by the way, I'm not sure how many of you are utilizing the TA's office hours. So the links for the TA's office hours are there in the course website. So you can go talk to the TAs any day. Probably you'll have more things to talk after today, like after we release the assignment. But this is my office hour, so I'll stay here until somebody kicks me out. If I go out, then probably we can go to my office. So thank you.